Good morning, everybody.
Good morning.
So today it will be we will have the last lecture, which is advanced CNN. It will be the last lecture where we will cover some advanced CNN architectures, and also maybe after maybe not next week, the week after, we can have one week also for just presenting. I mean, for you to present your main findings and your results. So maybe each one can use 10 minutes or 15 minutes maximum, for example. So we can try to cover as much as possible. So you can present your work and you can get some feedback from the class. So today we want to cover this last part, and at the end also we will revise what has been done this semester. But we can start first here. So today we will try to cover some CNN design, famous design, and also some understanding some advanced architectures, such as, some famous deep learning models, such as LeNet, AlexNet, VGGNet, for example, Inception, ResNet. So today we need to talk about those design pattern. There are three different types of pattern: feature extraction and classification. This is a traditional part, and which we learned last time. Pattern 2, which is image depth increases and the dimension decreases, and a pattern number 3, which is the fully connected layers. And we need to understand some advanced architectures such as LeNet, AlexNet, VGGNet, Inception, ResNet, etc. Yes, okay. So I don't know why it's not moving. Okay, so this pattern number 1, which is feature extraction and the classification. This is traditional one which we learned. So we have this part. It will be the feature extraction part. Right. So this one, it will be feature extraction part, and it consists of number of layers, which some conv layers is tagged to each other. For example, maybe we will have some conv layers followed by some other layers, such as pooling layers, for example. So it's number of conv layers followed by maybe average pooling or max pooling layers. And at the end of this feature extraction part, we will have the classification part. And this classification part, it will be a number of fully connected layers. This fully connected layers, it's just a traditional machine learning. It's like shallow learning. It's number of fully connected layers, similar to feed-forward classifiers, for example. So the features or the feature map, we will get here at the end some high-level feature maps, for example. We will flatten those feature maps and we will send it to the next layer, which will be fully connected layer. And the last part, which we call it the classifier, will do the classification part for us. Maybe this last layer, maybe in those fully connected layers, we will use some activation function similar to ReLU, for example. And in the last layer, what kind of activation function should we use here? It could be it's for classification. So we need to select. We need to select an activation function which fits our own data set, for example. So this pattern number 2, its image depth increases. As you can see here, we have this input image, for example, and this is the feature maps which we are extracting. And as you can notice here, that the depth increases as the dimension decreases, right? So the dimension, which is height and width, decreases with time, and the depth increases. So the input data at each layer is an image. At each layer, we apply a new convolutional layer over a new image, and each image is a 3D object that has height, width, and the depth. Depth is, we can call depth is a number of color channels, for example, which we have. When it's 1, it means it's a grayscale image, for example, when it's image, but it could be also something else. It could be a feature map. So when depth equal 1, it means it's a grayscale image, and when it's a 3, it's a color image, so RGB image, right? In later layers, the image still have depth, but they are not colors. They are feature maps. When depth increases here, we know that this one, it's not an image, but it's a feature map, right? This one is a feature map. And as you can see here, if this one is an input image, RGB image, for example, maybe the depth is 3, and when we go deeper, it's 55, for example. Sorry, it's 96, correct? Which means we applied here a kernel of size 11 times 11 times 96, or we applied 96 filters from this time. It's followed by maybe some max pooling, and at the end, after max pooling, we will get something, and after that we will apply another filter, which is 5 times 5. But how many of those? Maybe it's 256. So in this case, we will get this kind of depth. So the depth, in fact, it will be equal to the number of filters which we need to apply. So as you can see here, the dimension decreases and the depth increases. So it's one of the most famous design pattern which is used in developing those models. Number 3, it's fully connected layer, which we know very well. All fully connected layers in a network either have the same number of hidden units or decrease at each layer. It could be the same number of hidden units in each layer, but of course it might increase. I mean, it's more popular, or it's more general. That number of hidden units decreases over time, and it's rare to find a network where the number of units in the fully connected layers increases in each layer. So usually the number is fixed or decreases. I mean, similar to this example here. So the number of hidden units decreases, but not increases, right? So, this is, this is one of the most famous models. It's called the LeNet5, and it was introduced in 1998. And it consists of 5 weighted layers, and therefore it's called the LeNet5. LeNet5, because it consists of 5 layers. And it consists of 3 convolutional layers and 2 fully connected layers. So those 5 layers are 3 convolutional layers and 2 fully connected layers. So the feature extraction part consists of 3 convolutional layers, and each layer, in fact, it's followed by average pooling, as you can see here. So we start with conv layer, followed by average pooling. And after that, we will get another conv layer, followed by average pooling. And at the end, we will have a conv layer. And at the end, we will have, after this conv layer, we will have a feature map. We will flatten it, so it will be followed by flatten layer. And after that, this one, it's a flatten layer, correct? Which do nothing. It does not have any parameters. It will just convert those feature maps from its dimension, which is 5 times 5 times 16, to one-dimensional vector, which has a size of 120. And after that, we will have 2 fully connected layers, FEC1 and FEC2. And as you can see here, the number of hidden units decreases over time. This function, it uses a hyperbolic tangent as an activation function. So the activation function used here, it's hyperbolic tangent. Instead of today, for example, today we are using state-of-the-art ReLU, because in 1998, ReLU does not exist, in fact, was not invented at the time. So, this layer, it consists of 5 layers, and they use hyperbolic tangent as an activation function. So this function, in fact, it is used to classify, for example, MNIST dataset into one of those 10 classes, right? So maybe the last layer, it will be softmax layer, right? So this is, we need to train this model on MNIST dataset. For example, you can go to the example here. So this is the model. When we use this model.summary, we will get the details of the model. So the model consists of 3 conv layers. So this is the first conv layer. And this layer has 156 parameters, correct? The second conv layer, this one, and this one has 2,416 parameters. We have here a third conv layer. So in fact, it's a 3 conv layers followed by average polling. So this one followed by average polling. This one is followed by average polling. And finally, we will have the third conv layer, right? And it's followed by a flattened layer. And this flattened layer, it will do nothing except it will just convert the higher dimensional feature map or our high-level feature map from its dimension into one-dimensional vector. So it will be one-dimensional vector which contains 120 feature maps or features, for example. So after that, it will be, so this is the feature extraction part. We can say that this is the feature extraction part. And after getting our features, we will send those features to the classifier part. So this one, we can call this one, it's the convolutional part or feature extraction part, and it will be followed by classification part. So this classification part, it will try to classify each example or each image into one of those 10 digits, right? So the first dense layer, it has 84 hidden units, and the last the output layer, it has 10 hidden units, because we need to classify each image into one of those T classes. So we trained this one into an MNIST data set, and you can see this is a confusion matrix for the test set, and we can see that those numbers across the diagonal are very well, right? So the accuracy is really very high, and we can achieve an accuracy equal 98% or 98.7%, which is very good accuracy. And this model has been trained for 20 epochs, as you can see. So in this figure, we have the training and validation loss. This is very important. So at epoch number 1, we can see that the loss is very high. This one for the training, because it's higher than the validation, correct? And with time, those two will go down until maybe reaching very small value. So maybe if we can keep this model for more time, more few epochs, maybe we can achieve maybe 99.9% accuracy. So this is a training and validation accuracy. Also, you can see here that the accuracy, it was very low at the beginning, and when we started training the model, those accuracies will increase. You can see here, so we have a point here, in fact, where the training and the validation, okay, this is the validation, and this is the training, which is okay. You can see that here we have at some point, I mean, it's okay. I mean, there is no overfitting or something. I guess the accuracy is very, very good. So this is the performance of this LeNet 5. If you want, I mean, you can just go to this example and try to run it, or you can try to use it in your model. I mean, this model has only 61,000 parameters, right? Which is very small model. So you can, I mean, you don't need, in fact, to transfer this model from one domain to another domain. You can just train this model from scratch. Yes, please, Christian.
Oh, thanks.
Yes.
Can you say something about optimizers to train the network? Do you use the same optimizer for each layer?
Yeah, I guess I need to open this example, but
yeah,
okay.
I could do it too.
Okay, so
I recently saw a paper that about large language models, actually, but it was about the fact that the Adam optimizer, which is a lot used, actually have some deficits. So I thought that it's interesting also to think about the optimizer.
Yes, of course. Can you see
I
my
never
screen?
really thought that much about
the different. I mean, the difference between different types of optimizers. Yes. So can you see my screen? Can you see my code?
Yes.
Yeah. So I mean, this is my code. I just I mean, you can see here from keras.layers we imported conv2d, average polling, flatten, dense layers. We from sklearn.metrics we have confusion matrix, but of course we need to get other metrics like F1 score, for example, which is important. From keras.utilities we imported two categorical, because we need to convert the target features from its because it's 0, 1, 2 until 9. We need to convert its categorical, so we need to convert it into one-hot encoding. So I'm using this function to convert it into one-hot encoding. So this is the dataset. We imported the dataset from keras.datasets.mnist. We imported the data, and I divided each, I mean, xtrain and xtest by 255, because I mean, each pixel value has a value between 0 and 255. So just normalize it by dividing each pixel value by 255. And y-test has been converted from categorical into one-hot encoding using this function. So the dataset is already divided into xtrain and xtrain, xtest, y-train, y-test. I built the model. So this is the model. We have the first conv layer. It has 6 filters. So we select the number of filters equal 6. I mean, the kernel size is 5, which is 5 times 5. Stride equal 1. I use the hyperbolic tangent as an activation function. The input shape is 28 times 28 times 1 because it's grayscale image. Padding equal same. And it's followed by average pooling layer, which has, this pooling size equal to, stride equal to. So this filter here, it will be 2 times 2, the stride equal 2. So it's not overlapping. Padding equal valid. So the second conv layer has 16 filters, the same size also. So the inception field, it's the same, 5, kernel size is 5. So the kernel size, in fact, is the same size in the 3 layers, in the 3 conv layers. So the first conv layer, it's 5, the second is 5, the third is 5, but the first and the second are followed by average pooling. And after that, we will flatten as the output from the third conv layer, and the 2 fully connected layers. The first one 84 units, and the second one has 10 units. I mean, this one, when they trained this model in 1998, it was maybe a revolution at the time, because maybe at the time computational resources was not enough. So it was very good effort at the time, 1998. So also we used a hyperbolic tangent in the first hidden, on this only hidden layer which we have, right? And in the output layer, we have softmax. So the output layer, you can call it softmax layer because it will classify each image into one of those 10 classes. When we use model.summary, we will get those information. And here, this is model compile. I used the loss function categorical cross entropy. I used SGD, in fact, optimizer, stochastic gradient descent. So maybe if you can use something else, maybe you will get better results. Yes, so it has been trained for 20 epoch. And after that, we can just plot those training and validation accuracy and loss, as you can see it's here. And also we can plot the confusion matrix for the test set. But as I told you, you need to do more. I mean, maybe you need to calculate if one score, for example, maybe recall and we have accuracy. If one score, for example, and those numbers are very important to calculate. Yes, do you have any question for this code?
It's nice to see. It's a nice, very, very dense, short notebook, actually doing a lot of stuff.
Yes, but if you want to make more, we build the model from scratch. I don't think it's possible to get the model because other transfer learning models, we can import the model structure, but LeanIt, maybe it does not exist because it's very simple. So you can just build the model as it is shown here. So it's a very simple model, and it's called LeanIt 5 because it consists of only 5 layers. So for evaluation, model evaluation, I have here only the confusion matrix, but as I told you, it might not be enough, only the confusion matrix. Maybe you need to get this precision recall and F1 score, for example. Yes. So I will just move this one here. We will go back. Can you see my slides again?
Yeah.
Okay. So now, if you want to print some nice numbers, this is the model, and we trained the model, and we can test the model, and we can get the confusion matrix. Now we have the accuracy. It would be nice if you can get maybe precision recall F1 score, for example. But how to retrieve those filters or kernels and the biases? If you want to get those, if you want to see those numbers, because we know that the filters here, in the first conv layer, we have 6 filters, right? Okay, one more time. As you can see here, we have here in the first conv layer, we have 6 filters, correct? And each filter has a size of 5 times 5. right? In the second conv layer, we will have 16 filters, right? But the filters here, it will be 5 times 5 times 6. Why 6? Because the depth of the feature maps from this conv layer has a depth of 6, if you can remember. I mean, the third conv layer, it will be, we will have 120 filters, right? So the depth of the feature map here, it will be 120, but each filter will be 5 times 5 times 16. If we can go back to the code here, we just defined 5 here, right? One more, I mean, it was in the code, sorry. It was in the code, which I showed you last time, but we just defined here the kernel size is 5 times 5, right? No, it's not here. So this conv layer, the filter here is, each filter, in fact, has 5 times 5 in the 3 conv layer. But because the input image, it's grayscale, so the dimension of the filter of the first layer, it will be 5 times 5 times 1. How many filters? 6 filters. So, and after average pooling, we should expect that the output from average pooling, it will be 14 times 14 times 6. So the depth here will be 6 because the number of filters here equals 6. So in the second conv layer, when we need to define a filter, so the filter also will be 5 times 5, but because the depth of the feature map after average pooling is 6, so the filter size will be 5 times 5 times 6, correct? How many of those filters? It will be 16, correct? So if you need to calculate number of parameters here, it will be 16 multiplied by 5, multiplied by 5, multiplied by 6, plus 16, if you want to get this number. And if you get this number also, 156, it should be 5 times 5 times 1 times 6 plus 6. Can you try it, please? It will be 5 times 5. And how many of those? It will be 6. It will be 25 times 6, which is 150, correct? Plus 6 BIOS, it will be 156. So it's just, I mean, the filter size here, all filters here has the same size, which is 5 times 5. All kernels have the same size, which is 5 times 5, right? This one also, it's 5 times 5, but the depths will be different. The depths will be based on the feature map from the previous layer. So here, the depths, because this one, it's a grayscale image, so the filter says it will be 5 times 5 times 1. For the second layer, it will be 5 times 5 times 6, correct? Because the feature map from the average pooling, it will have a depth of 6. So the last layer also, the kernel, it will be 5 times 5 times 16, correct? Because the feature map from the second conv layer, it has a depth of 16, correct? So it's just if you want to plot some filters, for example, if you need to get access, or if you want to see how it looks like, maybe it's much better to just to select the first layer, because for the first layer, it will be 6 filters. Each has a size of 5 times 5, as you can see it here. 6, each has a size of 5 times 1. So we have here the 6 filters. So this is number 1, number 2, number 3, number 4, number 5, number 6, right? And this is pixel values. And as you know, when it's black, maybe it's close to 0. When it's bright, it's close to 1, right? And it's just this, I mean, I just try to print one of those filters for you. So it's a matrix which is 5 times 5, and it contains number of, bunch of numbers, right? And this is the BIOS because the first, for the first conv layer, we have 6, right? We have 6 filters. So this is one of those filters, and we have 6 BIOS. So this is the first value which connected with this one, for example, because we have 6 perceptrons. How can we do this? You just need. So, for example, for layer in model.layers, for example, you can print the layer name, correct? And if it's conv continue, because I'm interested to print out those for the conv layers. So I try to get those filters and the BIOS for each layer. It's layer.get weights. So filters, BIOSes equal layers, layer.get weight, for example. So if you want to get access to those filters, and after that, you need to put it as an image. You need to reshape it as 5 times 5, because I know that this one is 5 times 5. Just reshape it into 5 times 5 and try to plot it, for example. So now I can plot those filter, those kernels. So you can see that from the for the first conf layer, we have 6 filters, and each filter has a size of 5 times 5. So it's just an example if you want to get access to those numbers and look into it, because when we started this deep learning, we started with some filters from image processing book, if you can remember those edge detection, for example, horizontal and vertical edges, for example. So we have a filter which consists of bunch of numbers. It's the same. After optimizing this model for our problem, we got this kind of filter here, right? We have this filter. You can do the same before training your model, and before training your model, we just initialize those kernels with a set of random numbers, right? We just initialize it with a set of random numbers, and biases also are initialized with zeros. So if you want to do this for after initializing your model, after defining your model before training your model, and if you try to print out or plot those initialized kernels and bias, you will get something similar to this one. So this one, it's initialized just with random numbers. But after training, after 20 epoch, do you see those biases also, it's equal zeros. We have 6 values. This is one of those filters. It's just initialized with very small number, very small random numbers. And after training the model for 20 epoch, you will get this one, right? So this one will help you to get something which makes sense for our classification problem. And at the end, we can achieve accuracy of 98%, right? So when we initialize our model, we will get this kind of loss, right? We will get this kind of loss. We will get this kind of accuracy. And after 20 epoch, you can see that the accuracy has been improved, increased a lot. It's close to 1, for example. And also the loss after 20 epoch, it was very close to 0. The second model, it's AlexNet, and AlexNet was presented in 2012, and it's a series of convolutional and pooling layers stacked on top of each other, followed by fully connected layers and a softmax. So this is the traditional approach. So the first part here, it will be the feature extraction part, right? As we know, this one is feature extraction block. We can say it's feature extraction block. And the last part, it's the classification part, or the classifier. And the classifier, it's similar to feed-forward neural network. No difference. I mean, the addition here, it's just adding the feature extraction part to automate the process. Because, I mean, before using those deep learning stuff, it was for us, we need to try to dig into, we need to plot our feature sets. We need to try to use feature engineering techniques. But using the feature extraction, we automated this process, and we are working directly with images, with raw data, in fact. So this one, it's raw image or raw data. And we just use this feature extraction part to automatically extract features which make sense to our problem. So it's a series of convolutional and pooling layers stacked on top of each other, followed by fully connected layers and a softmax. We have here a softmax, and as you can see here, softmax layer, it classifies each input image into one, or each object into one of 10,000 classes, right? And as you can see here, for the first fully connected layers, number of hidden units it's the same, in fact. Right? Number of hidden units, it's the same. And after that, it will be followed by a softmax layer to classify each object into one of those 1,000 classes. And it's similar to LeNet, but it's much deeper. It's very similar to LeNet, but just deeper, which means we just have more hidden layers, because the other one, in total, it has 5, 3 conv layers and 2 fully connected layers. This one has more conv layers and more fully connected layers. So AlexNet has 60 million parameters and 650,000 neurons, which gives it a larger learning capacity to understand the more complex features. So this one has more learning capacity, better learning capacity, because it has more parameters. I mean, those large models today, for example, ChatGPT, it has billions of parameters. So this one, AlexNet, it has 60 million. And it's trained using ImageNet. This model has been trained using ImageNet, which is a visual database designed for use in visual object recognition. And this dataset consists of more than 14 million images categorized into 22,000 categories. So it's around 14 million images. More than 14 million images has been used for training this model. So just compare number of parameters at 60 million. And if you need to train those 60 million parameters, at least you need something like this one in this range, 14 million images. So this model consists of 5 convolutional layers and followed by 3 fully connected layers, which means it has 8 in total layers. It consists of 8 layers compared to LeNet, which is 5 layers. So the input image, it's RGB image, as you can see. The input, it's RGB, and it has a size or the dimension 224 pixels times 224 times 3, because it's RGB image. The first layer, it's a conv layer, which has a filter of 11 times 11. How many of those filters? It's 96, right? So if we need to calculate number of parameters here, it will be 96, which means the number of neurons here, it's 96 neurons, correct? 96 hidden units. Because here, I mean, he mentioned that we have here 650,000 neurons. How can we calculate this number? I mean, each filter is 1 neuron, correct? So it will be 96 plus 256 plus 384 plus 384 plus 256 plus this number plus, I don't know really if this number is correct. Yeah. This is strange. Okay. Maybe this number is not accurate, right? So yeah, so this is a model. So the filter here is a kernel of the first conv, it's 11 times 11 times 96. For the second conv, it's 5 times 5 times 256, correct? For the third, it's 3 times 3, correct? For the fourth, it's 3 times 3, and for the last one, it's 3 times 256. And as you can see here, we are starting from this input image, which is RGB image, which has 3 channels. And as we go, the depth increases and the dimension decreases. So at the end here, the dimension will be 13 times 13, but the depth will be 256. So this is pattern number 2, where we have the depth increases and the dimension decreases, right? So this is AlexNet in more details. I mean, this is 11 times 11, stride equal 4. It's 96 kernels, and each kernel is represented by 1 hidden unit or 1 neuron, for example. So the output from this one, it will be 55 times 55 times 96. It's followed by overlapping max pooling, which has kernel size equal 3 times 3, stride equal 2, 1 stride less than the dimension of the max pooling kernel. It means we have some kind of overlapping, right? So the output will be 27 times 27 times 96. The depth will be the same. It's followed by conv layer, which has 256 kernels. So as you can see here, the depth increases because we're increasing the number of kernels or number of filters, as the dimension decreases because we don't use, for example, zero padding, for example. We will do this until we finish here, until we got this feature maps, which is 13 times 13 times 256. And after that, we will flatten this one. It's followed also by overlapping max pooling. So it will go also down into 6 times 6 times 256. So this is the output feature map. As you can see, this is the output feature map. We will flatten it. When we flatten it, it will be converted into a vector of this dimension. So it will be one vector of this dimension 9216, right? It's followed by 2 fully connected layers with the same number of neurons in each layer. And after that, it will be followed by an output layer, which is a softmax layer, to classify each input image into one of those 1000 classes. Yes. So this is AlexNet. It's a very powerful model, and it has been used in many different applications. So we need to talk about transfer learning. So transfer learning, it's a transfer, a model, for example, which has been trained on a data set to a new data set, for example, if it is, I mean, within the same context, for example. So, for example, apply transfer learning to VGG16 network. We freeze the feature extraction part of the network and remove the classifier part. Then we add our new classifier, including a softmax layer with 2 hidden units. For example, a pre-trained network is used as a classifier or as a feature extraction. when the target domain is somewhat similar to the source domain. So if we can go back again, I mean, this model, this model has been trained using 14 million images. So in fact, you need huge computational resources to train this model. So one way, if you want to use this model, is to try to import the feature extraction part, which is that part, right? We will import that part to our problem, and we will change only the classifier, because maybe this AlexNet, it has been trained to classify each object into 1,000 classes, but maybe in my problem, I want to use this AlexNet for classifying MNIST dataset, which is 10 classes, right? So in this case, I will just change the classifier here. I will change maybe the softmax layer from 1,000 units into 10 units, and I will use it to classify MNIST dataset, for example. So if you want to do this, I need to import this model AlexNet. I want to freeze those weights of those feature extraction part, because if I will retrain that part, I will destroy the weights, right? Because I need to initialize those weights using random numbers, and I need to use my optimizer to adjust those weights. And maybe using MNIST dataset, it's not enough, because MNIST dataset, how many datasets? How many in MNIST dataset? What was the size? So now this one has been trained using has been trained using this ImageNet. This one has been trained using ImageNet, which contains 14 million images. If we need to train this model again using MNIST, so how many in MNIST? How many? Do you remember how many dataset in MNIST?
5,000, I think.
Huh?
5,000, is it?
What? What?
I think it's 5,000. I'm not sure.
Only 5 MNIST dataset. I don't remember. Maybe it's, yes, it could be 5,000 and 1,000 for testing, right? Because it's 10 characters, 10 characters, and each one, I guess, I don't remember. I need to search. I mean, the size of MNIST dataset.
MNIST is, I think, 60,000, 50,000 training and 10,000 test.
Yeah, correct.
Yes, 60. Yeah, 60,000.
Missing 10.
50,000 for training and 10,000 for testing, right? So it's 60K, correct? 60K, 50K for training and 10K for testing, correct? So I just compare between the ImageNet and MNIST dataset, for example. I mean, if this model has been trained using 14 million images, it will be very difficult really to train this model using MNIST. So it's a smart, in fact, to transfer this model from ImageNet into MNIST dataset. How can we do this? I mean, the most important and the most time-consuming part for us, it's the conv part. In fact, this is the conv part, which is a feature extraction part. So I just need to import this model into my application, and I just need to change this classifier, because this classifier here it consists of 10 layers. 3 layers, 3 fully connected layers. Maybe I can keep this one and the first 2 fully connected layers, and I need to change the softmax layer from 100 classes into 10 classes, correct? And that is it. And I will freeze the parameters of the conv part, because I don't need to touch that part, because this part works fine. Because this part, in fact, it can work with any image, and it will be able to extract a feature map, which makes sense. And because ImageNet is images, and MNIST dataset also it's images, so it's almost the same domain, correct? So we can say that, okay, I will try to transfer AlexNet into my MNIST classifier. I will use AlexNet to classify my MNIST dataset by importing the feature extraction part and just freeze it, because I don't need to touch it. And I will just change the classifier part. I will change the output layer from 1,000 neurons into 10, because my MNIST dataset, I need to classify each image into one of those 10 classes. I don't need to get the other 990 classes. I just need to classify each image into one of those 10 classes. So in this case, I just need to change the last fully connected layer from 1,000 to 10, right? So this is the story here. So this is my model, correct? So my model consists of this block, which is the feature extraction block, which is very complex, as you can see here. It consists of 5 layers, right? So I need to keep this one as it is, keep that part. and I need to change. In fact, I need to remove my classifier, and I need to change it with my own classifier, right? Because this classifier, it has been designed for classifying each image into one of those 1,000 classes. So I need to change this one into with another classifier, which can classify each image into one of maybe it's binary classification, or in case of MNIST, it will be 10 classes, right? So we just need to keep the fully connected. The feature extraction part, we need to keep it as it is, and I just need to replace the classifier with a new classifier. That is it. So in this case, in fact, I will freeze those parameters of the feature extraction part, and I will just train only my classifier, because my classifier is brand new. So this is brand new classifier. And this classifier, the weights of this classifier are initialized with some random values. So I need to train this classifier, right? I just need to train this classifier, and it will be fine. So do this, and if you got good accuracy, it's fine. If you didn't get maybe very high accuracy, you can do some fine tuning. And in this fine tuning, we try to because at the end here we have a feature map, right? Those feature maps will be generated based on the weights of the feature extraction part. Maybe for some reason it's not matching a lot to your problem. So in this case, you can do some fine tuning. And in this fine tuning, in fact, you can just select one, the last conv layer or the last two conv layers, maybe this section, and try to adjust those weights as well. Not the whole block, but only maybe the last layer or the last two conv layers. This is fine tuning. So the most radical way, in fact, will be to freeze the weights, all those layers. We will freeze the weights of those all the conv layer part. So we will freeze the feature extraction part, right? Like by 100%. We will not retrain that part. We will freeze all those weights, and then we will train only the new classifier, which we just added. We will remove all the classifier, and we will add our own classifier. And because it's a brand new classifier, we will initialize those weights with some random values, and we will train the whole model in this case. So I will freeze the weights of the feature extraction part, and I will retrain the whole model. And in this case, we will train only the classifier part, because that part is frozen, right? In this case, we will train only that part. But if you still don't have the accuracy which you want to get, in this case, we can do some fine tuning. And in this fine tuning, we can just select one or two layers, two conv layers. The last conv layer, for example, or the last two conv layers, and try to retrain those two layers, for example, right? Not the whole, but only maybe the last layer or the last two layers, because I don't have enough data for training the whole part. So it's just you try to fine tune the feature maps, because I'm getting here a feature map. Maybe this feature map is not very suitable to your problem. So in this case, you can just train only one layer, right? One or two layers. And in this case, we call it fine tuning. And in this fine tuning, it will try to readjust the feature maps to fit your problem better. So fine tuning a pre-trained network, if you are freezing the convolutional layers only, then you are using the pre-trained network as a feature extractor and transferring all of its high-level feature maps to your domain. If you will freeze the whole convolutional layers, in this case, we will be using the pre-trained network as a feature extractor, and it will transfer all its high-level feature maps to my domain, right? If you did that, and if you still don't have the accuracy which you want, in this case, we can try to do some fine-tuning. And in this fine-tuning, we will freeze a few of the network layers that are used for feature extraction, and we will jointly training both the non-frozen layers and the newly added classifier layers of the pre-trained model. And it's called fine-tuning because when we train the feature extraction layers, we fine-tune the higher order feature representations. In this case, you will try to fine-tune those high order feature representations to make them more relevant for the new task dataset. So maybe we will freeze the first, the second, the third, and we will go to this fourth, and we will unfreeze it, and then we will train it with my classifier. So in this case, we will try to fine-tune the higher order feature representations which we are getting from the feature extraction part. So it's a kind of fine tuning. But of course, I mean, it will come at the cost also of computational time. So this is a model. We try to fine tuning, for example. So for example, I mean, this is the input image. This is, I mean, the feature. We have here a conv layer, and it will get a feature map. We will have another conv layer. We will get another feature map 2, feature map 3, feature map 4. So you need to decide by yourself where you want to freeze. So maybe someone, he will say, okay, I will freeze here. Maybe someone, I will freeze here, for example. I will freeze here or here, for example. When you do it here at the end here, it means you will use the pre-trained network as a feature extraction without any fine tuning. But you can decide that, okay, I need to fine tune. I need to retrain maybe the last conv layer to try to readjust the obtained higher order feature maps to fit my problem better. So this is the whole story. And in this case, in fact, when we try to code this one, we will get number of trainable parameters and the number of non-trainable parameters. Trainable, it's the parameters which we will train, and non-trainable, it's the parameters which are frozen. So this is just an example. Feature maps extracted from our models that are trained to classify faces, cars, elephants, and chairs. For example, I mean, this is kind of feature maps. You see that, I mean, transfer learning, it's nice approach. For example, we train a model on faces, for example. This is the feature maps which we are getting. If you train your models on cars to classify cars, for example, you will get this kind of feature map. You can see that it's very similar to the feature maps obtained for faces, for elephant as well, and for chairs. As you can see here, feature maps are almost similar, right? Feature maps from faces, from cars, from elephants, from chairs, almost, it looks like similar, correct? Which means in this case, I can transfer a model which has been trained on faces to classify chairs. I can train a model which has been trained to classify elephants to classify faces or cars, right? Because I mean, in this feature extraction part, we are not classifying, but we try to extract those higher order feature representations, which can help me to solve my problem. So what is the meaning of those? I mean, when we transfer a problem from one domain to another, what is happening? In fact, we just transfer those kernels, correct? If you can remember those kernels, the convolutional kernel with optimized weights. We try to transfer this one from one problem to another problem. So, for example, I can train my model on faces data sets, for example, and I will train the feature extraction part. And we will, when we train that part, in fact, we will optimize the kernels filters, right? When you optimize those kernels, you will get those kernels with those optimized weights. And this one, I can get this one, for example, I can transfer this one from faces to elephants or to cars, for example, right? So I will train my model on faces. And when I train my model on faces, I will get those higher order feature maps. To get those higher order feature maps, you need to train your model. And when we train our model, we will optimize the weights of the kernel, convolutional kernels. So, and when we transfer it from one problem to another problem, we just transfer those kernels, correct, those optimized weights. So this is what we transfer in reality. So I can optimize this one from on a data set, and I can use it on another data set. I can do it. I can obtain it from faces and apply it to cards, for example, or elephant or cards. Yes, please. If you have any questions, just please you can ask if you have any questions. So this is the this is the convolutional kernel. I mean, if you can remember here, those are the kernels, right? Those are the kernels which we are getting, right? Those are the kernels when it's 5 times 5, right? Maybe it's difficult to understand the meaning of it, but I mean, it's the same principle. Yes. Now we have this VGGNet. VGGNet, it was developed in 2014 by this visual geometry group at Oxford University. And the building blocks are exactly the same as those in LeNet and AlexNet, except that VGGNet is more deeper, with more convolutional polling and dense layers. It's just more deeper. I mean, AlexNet, it was 7 layers, correct? I mean, we can start with, again, with LeNet. LeNet was 5, and AlexNet is 8 layers, correct? So LeNet was 5, and AlexNet was 8 layers. And VGG net, it's how many layers? We have here 2 types. We have 2 variants, VGG 16 and VGG 19. And 16, it means it has 16 layers, and the VGG 19, it has 19 layers, which is much, much deeper compared to AlexNet. So VGG 16 consists of 16 weighted layers, 13 convolutional layers, followed by 3 fully connected layers. And the VGG 16 has unified receptive field. Unified receptive field, which means each convolutional layer has the same filter size. So in first conv layer, it has 3 times 3, second is 3 times 3, and each layer has the same receptive field, right? It's just unified, right? As you can see it here. So, and it consists of 13 convolutional layers, followed by 3 fully connected layers. The fully connected layers also, it has the same, it's very similar to AlexNet, so it has the same number of hidden units. The first 2 fully connected layers, and the last fully connected layer, or the output layer, it's softmax layer, which can classify each object into one of those 1000 classes. So this is the receptive field, which is 3 times 3. It makes life maybe much easier, right? And of course, this one uses ReLU activation function. So VGG 16 as a feature extractor for fashion, if I need to transfer VGG 16 from one domain to another domain, so I can just, this is just an example. This is my base model, VGG 16, but I don't like this way for doing it, in fact. So I will go to the second one. Yes, I like to import it like this one as one line, in fact, as one layer, but we can just explain this one. So this is my base model. It's a VGG 16, and I need to download this classifier without the top part, without the classifier, because I need to apply this one to another problem domain. So we download this one. It's a VGG 16 with equal ImageNet, which means this model has been trained using ImageNet, which consists of 14 million images. Include top equal false, which means I just importing the feature extraction part. I mean, this one is very important. Include top equal false, which means we will not include the classifier. It's only the feature extraction part. This is the input shape. It's 32 times 32 times 3, because this fashion MNIST data set, each image has a size of 32 times 32, and the depth equal 3 because it's RGB image. This is the minimum for this model, in fact, or maybe, I don't know, maybe this is for this VGG 16. It can be applied, I mean, it has been trained on something like this one. So this is the base model dot summary. If you want to give the summary of the model, now we need to freeze the feature extraction part, and I need to add a new classifier. So for this model, in this base model, for layer in base model dot layers, layer dot trainable equal false. In this case, we will freeze all those weights of each convolutional layers. Okay, base model dot summary. I don't know why I wrote it again. So now I need to we need to save the output of the last. Okay, I need to get the output from this feature extraction part. So last layer, or the output from last layer, it will be base model dot layer get layer. I mean the output from this block 5. I mean I need to get this summary because I need to know the name of this one, in fact, right? Because I need to get the output. This is the feature map. This is the feature map. If you want to get the feature map, you need to do it like this one. So I need to get the output from the base model dot get layer, and this is the last output, last layer. So last output, it will be last layer dot maybe dot output. I will flatten this output. Last output, I will flatten it, correct? And after that, I will add two dense layer. The first dense layer has 64 units, which uses ReLU activation function, and the output layer, it will be softmax layer, which has 10 units, because I need to classify each image into one of those 10 classes. So now I need to build a new model. So the new model, I will use model API. So new model equal model. Inputs, it will be the input to the base model, right? Inputs equal base model dot input, and the output equal X. And this is model summary. So this is the model. As you can see here, this is the input layer. The size of the input image is 32 times 32 times 3 RGB image. Block 1 conv 1, block 1 conv 2, max pooling, right? We have here it's followed, it's 2 conv layers followed by max pooling, 2 conv layers followed by max pooling, 3 conv layers followed. I mean, they call it block 1, block 2 because this is block 1. I mean, this one will be block 1, right? And each block, it's number of conv layers followed by pooling layer. So this is block 1, right? This is, I mean, you just give it any name. So it's block 1. We have here block 2, which is 2 conv layers followed by pooling layer, max pooling. It's block 2. And after that, we will have 3 conv layers followed by pooling. We will call it block number 3. We will have block number 4 also, which is 3 conv layers followed by max pooling, block number 4, and finally block number 5, which is 3 conv layers followed by max pooling, right? So if you want to get the output, I mean, if you want to get the output from this last layer, I mean, you need to remember the title of it. I mean, its name, which is block 5 underscore pool, correct? Yeah, so it's a block 5 underscore pool. If you want to get the output from this layer. Now we have flatten. We will flatten the output from the 512 pixel values or feature maps. We need to flatten it. And after that, I will add 2 fully connected layers. So the first dense layer has 64 units. And the softmax layer has 10 units because we need to classify each image into one of those 10 classes. So we trained the model using 20 epochs. And this is the training and the validation loss. And this is the training and the validation accuracy. But I have also, I mean, I don't like this kind of implementation. In fact, when we try to implement this VGG16, for example, and I prefer to make my code compacted. And in this case, you can just define sequential API, a model. I mean, sequential. You implement your model as a sequential API. So model equals sequential, and import VGG16 as one layer. So model add VGG16 include top equal false, weights equal image net input shape. So in this case, in fact, we will import VGG16 as one layer, right? We imported the whole model as one layer, and include top equal false, which means we will just we only import the feature extraction part. We will remove the top part, which is the classification part, and it will be followed by flatten. Now it's one layer. It will be followed by a flatten layer, correct? And after that, it will be followed by 2 fully connected layers. So as you can see here, the model, it's much easier. So the model now consists of 4 layers: VGG16, flatten, dense layer, dense layer. This is the number of parameters of the feature extraction part, right? And usually this number will be, if we will freeze this number, it will be non-trainable, correct? Can you see it here? We have this number exactly the same here, non-trainable, because we freeze that part. How can we freeze it? So it will be model, because this is my model now. I call it my model, which is very simple. So now I need to freeze the parameters of the feature extraction part. So it will be model dot layers 0 between square brackets dot trainable equal false, which means we will freeze the parameters of the feature of layer 0. Layer 0, it consists of VGG16. Now the model, I mean, the code is very simple and it's easy to understand. Flatten does not have any parameters. We have the first dense layer, it has 64. If you need to get this number, it will be 64 times 512 plus 64. If you want to get this number of parameters, it will be 10 multiplied by 64 plus 10. You will get this number. So at the end, total number of parameters will be 14 million, 14.7 million parameters. But trainable parameters will be only 33,000. Only 33,000 will be trainable. This number, in fact, which is the number of parameters of the fully connected layer 1 and the fully connected layer output layer, or fully connected layer 2. So this 33,452, in fact, it's the number of parameters of dense layer 1 and the dense layer 2, right? And the rest will be non-trainable. Now I'm training the model again, and as you can see here, I mean, it's almost the same performance as this one, but the code here, it's much compacted, right? So it will be very nice if you, I mean, when you are implementing VGG16 or any transfer learning model in sequential API, I mean, the code will be much, much easier. So this is the confusion matrix. We will not judge the performance of the model because it has been trained only 20 epoch. And also this model is, I mean, this number of parameters is too much, right? Maybe it's I mean, I don't know. because as you can see here, it's maybe it's overfitting or something, because this is a validation loss increasing, and this is also the validation accuracy decreasing, correct? So maybe this model is overfitting my data set, right? So the performance, it's expected to get this bad performance, in fact, on the test set, right? So because this model, you can just say that we used the 60,000 images for training 33,000 parameters, right? Which might not be, I don't know. If we can compare this one with LeanIt, for example, I mean, with LeanIt, we can get much better results here, right? When we trained it on MNIST dataset. Number of parameters here, it's 61,000, right? 61,000. So I don't know, in fact. And this model has been trained using 20 epoch. So the performance here is much better, right? Compared to this larger model, VGG16, for example, right? So this is the VGG16. If you want to import the VGG19, there is no difference. I mean, VGG19, it will be just 3. It will be much more deeper than VGG16. It will consist of 19 layers, right? Do you want to take a break, or should we continue? Do you want a break, or we can just continue?
I think a short break would be nice, but I don't want to decide for everyone.
Okay, yeah, thank you. So we can just take maybe 10 minutes break?
Sure.
And after the break, we will go to this Inception network.
Good.
Okay,
Thanks.
Thank you. So we can just meet after 10 minutes. Thank you very much.